Hello everyone, welcome to the second part of our Regents review series. In this video, we are going to talk about measurements. So what are measurements, or how do we collect measurements in science? So there are two types of measurements that we can have in any type of science. We can either have a qualitative measurement, so this is when we don't have any numbers, we just express a quality of that object. For example, if I'm saying that this substance or this object is tall, that is a qualitative measurement. However, the more common types of measurements in science are the quantitative measurement. This is when we have a specific number to represent that specific measurement. For example, if I say that this person is 6 feet tall, that is a quantitative measurement. Now notice that, and always keep this in mind, that units are super important for your quantitative measurements. So if instead of saying 6 feet tall, if I just say that this person is 6 tall, we don't know what that means. So you have to include your unit to represent or to be super clear about what you mean by a measurement. So the problem with quantitative measurements that we can sometimes have in science is that we might end up with these two numbers that you see on the screen right now. These are huge or like very large or very small numbers. So how do we write these numbers in a more efficient way? We use something that is called an exponential form or a scientific notation. And here is the general kind of formula to write a scientific notation. So this first part, the x point y, that represents a decimal number, and we call this a coefficient. Super important thing to remember about your coefficient is that this number must be between 1 and 10. Okay, and then we have the coefficient, we do times 10, which is the base, and then we have the z at the top, which is your exponent. The exponent depends on how many times we are moving our decimal and in what direction to write our scientific notation. We'll talk about what this means in a little bit, but just so you know what the scientific notation for the two numbers at the top is going to look like, it's going to be this. So let's talk about the rules for converting a given number into scientific notation. The first thing that you're going to do is write your coefficient. So we start with the first non-zero digit, because remember, this number has to be between 1 and 10, so it cannot be 0.9 or something. So we want the first non-zero digit to be before the decimal. Then we put a decimal, and then we keep writing the numbers until we have the last non-zero digit. So for example, in the 602 number, our first non-zero digit is 6, and the last non-zero digit is 2. So we have to write 6.02 in our coefficient. Then we do the exponent. So this depends on the number of times we move the decimal. And here's a general rule for moving the decimal. If we are moving the decimal to the right, then our exponent is going to be a positive number. And if you're moving the decimal to the left, then our exponent is going to be a negative number. So here's how we do this. So if you look at this number right here, we are going to, let me very quickly, no, where's my annotation? I want the pen. Okay, here's my pen. And yeah, I should stop that probably. All right, so okay, I got it. All right, so here is our number that we are looking at. So we said that our exponent is going to be, coefficient is going to be 6.02. And then we do times 10. Now we have to move the decimal. When we are moving the decimal, we start with where the decimal is right now. So right now it's after 6. And we want to include all of the numbers that we have after the 6. So we are going to start moving our decimal to the right. So this is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So this is our decimal after we have moved the decimal to include the entire number. So we have moved it 20 times to the right. So because it's moving to the right, it's going to be positive 20 for the coefficient. Okay, so then here's our second number. Now, when we write the coefficient, remember we have to include our non-zero digits only. So it's going to be 1.09 times 10 to the power of. Now this times our decimal is right here. So we're going to move it to the left. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So we have moved our decimal 13 times to the left. So that's why it's going to be negative 13. This is how you go from a given number to a scientific notation. But sometimes you might also be given the challenge of converting a scientific notation into a number. So how do we do that? You look at your exponent because you already have the coefficient, right? So you write your coefficient and now you look at the exponent to figure out which way do you want to move your decimal. So if you have a positive exponent, then you want to move your decimal to the right. So it's the opposite of what we did earlier, or just like kind of backtracking. So we have the same thing that we did earlier. And if we have a negative exponent, then we move it to the left. So remember that we might have to add the zeros because in the previous one, we were kind of getting rid of the zeros and just putting that in the exponent. So here we might have to add the zeros. So here's our first example. Let's look at this one. By the way, you cannot write your scientific notation like this because your 3 must be 3.0. So just keep that in mind if I ever ask you to write something in scientific notation. So, all right, so we have 3.0, and then we can, let me write this maybe. Okay, let me write this over here. So we have 3.0, and then your exponent is times 10 to the power of 4. So that means we are going to move our decimal 4 times to the right. So 1, 2, 3, 4. So this is where your new decimal is going to be. So the number becomes 3, and then we have 1, 2, 3, 4, 0. So that's 30,000. Here's another example. We have 2.1 times 10 to the power of negative 3. So because it's a negative exponent, that means we're going to move it to the left. So 1, 2, 3. This is where the decimal is going to be now. And then this empty space that you see, we're going to fill that with the zeros. So your final answer is going to be 0.0021. Alrighty, so this is how you go from scientific notation to a number and number to scientific notation. So let's look at some of the other things that you might be asked to do with scientific notation. So that includes doing some calculations with the scientific notations. I'm just going to pull all of that together. All right, so if we are asked to multiply two numbers that are written in scientific notations, you go ahead and multiply your coefficients, and then you add the exponents. For the division, you do the same thing, divide the exponents, but instead of adding the exponents, we are going to subtract the exponents. So let's look at some examples. So here you have two numbers in scientific notation and you're supposed to multiply them. So when you multiply the two coefficients, 2 times 3, you get 6.0, and then you're going to do 3 plus 4. So that gives you 7. So your answer is going to be 6.0 times 10 to the power of 7. Here you have two numbers given in scientific notation and they are dividing. So you do 10 divided by 5, that gives you 2. And then you have 5 minus 2, that gives you 3. So the answer is going to be 2 times 10 to the power of 3. What if you're asked to add or subtract two numbers given in scientific notation? So a very important thing to remember about adding or subtracting your scientific notations is that you want to make sure that you have your numbers written in correct scientific notation. Here's what I mean by that. So here you have the two numbers that are given in scientific notation, but they are not in correct scientific notation because this first number that you see is does not have its coefficient between 1 and 10. So that's why the general rule that we follow whenever we are trying to add or subtract two numbers in scientific notation is that we want to make our exponents the same. So make your exponents the same. So if in this case, this one looks like the correct scientific notation. So maybe we'll just, we agree with this one. So we'll go ahead and try to make the other one, the other exponent 10 to the power of 3. So if I want to make this 3 times 10 to the power of 3, here's the general rule that we follow for something like this. If you are decreasing your exponent, you're going to have to move the decimal to the right. But if you are increasing your exponent, you're going to have to move the decimal to the left. So in this case, because we are increasing the exponent, we are going to be moving the decimal to the left. So this number becomes 4.55 times 10 to the power of 3. So as you can see, this is now a correct scientific notation because 4.55 is between 1 and 10. So you take this number and you add that to this number. So this is very easy because you just add or subtract your coefficients. Your exponents are always, already the same. So that's going to be, we just keep that exponent. So it's going to be 7.05 times 10 to the power of 3 in this case. Okay. So the next type of measurement or measurement calculation, I should say, that you might be asked to do is unit conversion. So you might be given a unit and you might be asked to convert that unit into a different unit. So the thing about units is that we have something called the International System of Units. So these are the units that is developed and used in science everywhere in the world. So we are given some of those units in table D. So just in case you might want to find the unit of something that we have learned in class, and let's say you forgot the unit, some of those units are given in this table. And then for these units, we also use the prefixes sometimes to make those units bigger or smaller. For example, the unit of length is meter. So I might, if I just say meter, that's your regular unit. But if I make it by combining it with the prefix kilo, now I'm making it a bigger unit. So kilometer is bigger than meter. If I combine this with a millimeter, which is 10 to the power of -3, millimeter is smaller than the meter. So sometimes what can happen is that I might give you something in meters and I might ask you to convert it into kilometers, or I might give you something in kilometers and I'll ask you to convert that into millimeters. So to do something like that, if you are asked to convert a smaller unit to a larger unit, or vice versa, we use a procedure called dimensional analysis, your favorite thing. I know how much you all love this. So let's talk about the very basics of dimensional analysis. So here I gave you something in meters, and I'm asking you to convert this number into millimeters. So here's what we are going to do. There are 3 steps for dimensional analysis. The first thing that you're going to do is figure out something called a conversion factor. Meaning, if I want to figure out that when I'm going from meters to millimeters, how many millimeters do I have in a meter? Or how many meters do I have in a millimeter? So to do that, let me erase this and start with the first step, which is an easier way to write your conversion factor. So you're going to look at the prefix that you see in this case. So our prefix is milli. So you look at your prefix table and you see that milli is 10 to the power of -3. Okay, so all that you have to do now is put your unit with this prefix on both sides. So when I put the unit with the prefix on both sides, I know that 1 millimeter, so your unit in this case is meter. So 1 millimeter is going to be equal to 10 to the power of -3 meters. So again, meters is your unit. So this right here is your conversion factor. That's your first step. The second thing that you want to do now is you start with what's given in the question. So that is 0.0000005 meters. And you multiply that with your conversion factor. Now, here is a super, super important thing to remember about the conversion factor. You have to make a decision about which thing out of the two parts of your conversion factor do you want to put at the top and which thing do you want to put at the bottom. So do I put the 1 millimeter at the top or do I put the 10 to the power of -3 meters at the top? If I go ahead and put 1 millimeter at the top and the 10 to the power of -3 meters at the bottom, this is going to work perfectly because here's what I can do. I can go ahead and cancel out the meter with the meter. So now the only unit that I'm left with is millimeters. That means whatever answer I get is going to be in millimeters. However, if I do this the other way around, if I put the 1 millimeter at the bottom and I put the 10 to the power of -3 meters at the top, I won't be able to cancel the meter with the meter. So this is the trick of dimension analysis, that you have to cancel the units. So make sure that if you want to cancel the meters, you put the meters at the bottom so that you can cancel them out. So if you do this math, your answer, I believe, is going to be about 0.05, or is it? No, that's 0.0056 millimeters. All right, so let's very quickly review the 3 steps that we followed here. So we said the first step of dimension analysis is to determine the conversion factor. The second thing that you do is you start with what's given in the question. And then your third thing is to arrange your conversion factor or multiply your conversion factor with the given thing. But remember, you want to cancel out the units. So if you want to cancel the meters, you want to put 10 to the power of -3 meters at the bottom. So we can cancel the meters with the meters. By the way, for the math part in this question, you are going to divide, in case someone was wondering this. So you are going to divide the 0.000056 by 10 to the power of -3. So that's what gave you the 0.0056. All right, so this was your dimension analysis. Let's move on to the next thing about measurements, and that is significant figures. So significant figures basically consist of all of the numbers in your measurement that you are 100% certain of. And then we always include 1 digit in the measurement that is estimated. Here's what I mean by that. If I give you something and I ask you to find the length of that, maybe I give you a pencil and I ask you to find the length of that pencil using your ruler. Now we all know that our ruler has the measurements that look something like this. So you have your, come on, my pen is not changing color. Okay, so you have your, I'm gonna just do like 9. So you have the 9, and you have the 10, and then you have 9.1, 9.2, 3, 4, 5, 6, 7, 8, 9, and then there's your 10. So let's say that the length of your pencil, and this is centimeter, by the way. So let's say your pencil is, the length of your pencil is somewhere around here. Now, if I ask you to measure this, some of you are going to record this as 9.7 centimeters. Some of you might record this as 9.65. Some of you might record this as 9.68 or 9.69. So what's happening here, and those of you who might say 9.70, what's happening here is that everyone is kind of pretty much sure that this is 9.6, right? People who are saying 9.7, if they don't include the 0, then they're saying that their 7 is estimated. These people over here who are saying 9.68 or 9.69, they are saying that they're 100% sure that this is definitely 9.6, but they're not quite sure about the 8, because it could be 8, it could be 9, it could be 7. right? So there 8 and 9 is the uncertain digit or the estimated digit. So this always happens in our measurements. So significant figures kind of gives us the rules of how many digits should we include in our measurements to make sure that we have all of the certain digits and we have at least one estimated digit. So there are some rules that we follow if we are trying to count the number of significant figures in any given measurement. The first rule is that any non-zero digits that you see, they are always significant. Any zeros that you see between the significant digits or between the non-zero digits are also significant. Any zeros that you see at the beginning of a number are not significant. Any zeros that you see at the end of your number, their significance kind of depends on whether a decimal is present or not. So if the decimal is present, then they are significant. But if the decimal is not present, then they are not significant. So if you are okay with just remembering these 4 rules, go for it. That's excellent. But if you think you might be struggling with, or you might struggle with remembering the 4 rules by themselves, we do have a shortcut for you to count your number of sig figs. By the way, this is a very important scale, so please make sure that everyone knows how to count the significant figures. There is kind of like a 99.9% chance that you are going to have at least one question on significant figures on the Regents exam, so please do not get that one wrong, okay? So here's the shortcut to count the number of significant figures. It's called the Atlantic Pacific model because we can think of the map of the US and then think of where do we have the Atlantic Ocean and where do we have the Pacific Ocean. So here we have the Atlantic and here we have the Pacific. So your decision or this whole method kind of depends on the presence or absence of the decimal. So you first look at your given number, you see if the decimal is present or absent. If the decimal is present, then you are going to start counting your significant figures from the Pacific side. If it's absent, you're going to count your significant figures from the Atlantic side. So as you are counting, then you start drawing your imaginary arrow from whichever coast you are starting from, Pacific or Atlantic. And then once, so let's say your decimal is present, you start making your arrow from the Pacific side. If the decimal is absent, then you start making your arrow from the Atlantic side. And then you are going to start counting the number of significant figures when you hit the first non-zero digit. So here's what I mean by that. You have this example, 62,100. This number does not have a decimal. So if I want to count the number of significant figures in this number, I'm going to start making my arrow from the Atlantic side because again, the decimal is absent. So here is, I start making the arrow. The first number here is a 0. It's a 0. So remember, we do not start counting until we hit the first non-zero digit. So we're going to keep moving on. Keep drawing your arrow. The next number is also a 0. We keep moving. The next digit is a 1. This is a non-zero digit. So this is where we start counting our significant figures. And then we count everything after that. So this 1 is a significant figure. The 2 is a significant figure. The 6 is a significant figure. So in this number, we have 3 significant figures. Okay. By the way, remember that the moment you hit the first non-zero digit, you're going to count everything after that. So if I give you a number like 602,100, we are once again going to start from the Atlantic side because there's no decimal. Do not count the first 0. Do not count the second 0. Keep moving. And we start counting when we hit the first non-zero digit. So we count this 1, we count the 2, we count the 0, because remember, it's between your significant digits. So, and just the basic rule that you have to remember is the moment you hit the first non-zero digit, count everything after that. Doesn't matter if it's a 0 or whatever, just count everything after that. Okay, so and then we also count the 6. So this is going to be 4 significant figures in this number. Alrighty, so this is how we count the number of significant figures. Now you might also be asked to do some calculations involving where you have to take care of how many significant figures you must have in your answer. And of course, I forgot to add animations to these questions, but that's okay. So let's talk about the multiplication and division first. You are going to go ahead and multiply or divide just like usual. And then your answer, here's the rule that you want to remember. Your answer must have the same number of significant figures as the measurement that has the least number of sig figs. Okay, so if your answer has more sig figs than what you should have, then you can just round it to the correct number of sig figs. If it has less significant figures than what you should have, then you just add a 0 or a decimal to make sure that you have the required amount of sig figs. So let's look at this example. We have 7.55 times 10 to the power of 0.34. When you do the multiplication, you get 2.567 meters. So let's count the significant figures in this case. The first number that we see, 7.55, has so the decimal is present, meaning we count from the Pacific side. So this one has 1, 2, 3. So 3 significant figures. Then we look at the second number. Once again, decimal is present, so we count from the Pacific side. 0 will not be counted because we don't start counting until we hit the first non-zero digit. So we start counting from the 3. So the 3 and the 4, we have 2 significant figures here. Okay, so out of the 3 and the 2, because 2 is the smaller number of significant figures, our answer must have 2 significant figures. However, let's count how many we have right now. So we start from the Pacific side because decimal is present. 2 is a non-zero digit, so start counting from 2. We have 1, 2, 3, 4. Right now we have 4 sig figs. Because this is more than what we should have, we are going to round this number to 2 significant figures only. So that means we want to keep the 2 and we want to keep the 5. But remember, the number right after 5 is a 6. So that means when we are rounding the 5, it can become 6. So our answer is going to be 2.6 meters. So this answer right here, right now, has 2 significant figures. All right, so let's look at the addition or subtraction. In this case, once again, we add or subtract like usual. And then the rule for significant figures is that our answer should have the least number of decimal places given in the question. Again, the same rule. If we have more, we round them. If we have less, we add 0 or decimal. So looking at this example that you're given, if you do the addition, your answer is going to be 369.76. Decimal places are the number of digits after the decimal. So in the first number, we have 2 decimal places. In the second number, we have 1 decimal place. In the third number, we have 2 decimal places. So out of all 3, 1 is the smallest. So that means our answer should have 1 decimal place only. So in this case, if you look at your answer, we have 2 decimal places. So that means you're going to have to round this. So the 7, after it's rounded, is going to become 8. So our answer is going to be 369.8 meters. Right? So just remember that for multiplication and division, we are going by the least number of sig figs. And for addition and subtraction, we are going by the least number of decimal places. Alrighty? So let's look at some other things related to measurements. Sometimes what can happen is after we do a measurement, we might have some uncertainties in our measurements, which can depend on a lot of things. It can be instrumental errors, it can be human errors, a lot of things that can lead to uncertainties in our measurements. So let's say we are doing an experiment and we did 3 trials of that experiment. The reason why we did 3 trials is because we want to compare how much of a human error we might have made, right? Or just to see how much of the difference do we have between our 3 trials. So when we compare that difference between the 3 trials, what we are doing is we are measuring the precision of our measurement. So precision is how close our measurements are to each other. So let's say that after the first trial, the measurement that we got was 3.5. After the second trial, we got like 3.6. And after the third trial, we got like 4.5. So now what you can tell looking at these trials is that the first and the second trial are somewhat closer to each other, but for the third one, we might have done something wrong. So the precision is like very off in this experiment. So that is one type of uncertainty that can exist in our measurements. The second thing that we can do is we can go ahead and take the average of our 3 trials to get something that we call the experimental value of our experiment. So this is going to be the final result of our experiment, what we calculated. And then we can go ahead and compare this with the accepted value. So accepted value is something that comes from the industrial value, or that comes from the experimentation that other people might have done, or that is the value that is widely accepted for that specific object that we are measuring. So when we are doing this, when we are comparing our accepted value or our measured value with the accepted value, we are trying to find the accuracy of our experiment. So accuracy means how close our measurement is to the accepted value. So the calculation that we do to figure out the accuracy of our experiment is calculating the percent error. And the good thing about this is the equation for percent error is given in table T. So let's look at a very, very quick example of finding the percent error. So let's say a student determines the electronegativity of the element fluorine to be 3.6. What is the percent error? In this question, I already gave you the electronegativity, the actual electronegativity of fluorine as 4.0. Sometimes what might happen is that they might not give you the actual electronegativity of fluorine, and that's because you are given the electronegativity values in table S. So if that ever happens, where they have not given you the accepted value of something, just remember that the reason for that is because that thing is given somewhere. So look through your reference table to see where that quantity is given. All right, so we're just going to go ahead and plug in these numbers into the equation. So to find the percent error, my measured value in this case is going to be 3.6. And then the accepted value is 4.0. We divide this by the accepted value, which is 4.0 again. And then do not forget to multiply with 100. When we do the math, what you're going to notice here is that 3.6 minus 4.0, that is going to give you a negative number. So it's going to give you like negative 4.0 over, sorry, not negative 4.0, that should be negative 0.4 over 4.0 times 100. So the very, very important thing to remember here about percent error is that this is an absolute value. So percent error is an absolute value. You cannot have a negative percent error. So please always report your percent error as a positive number. So when we do the math for this, you should get 10%. Please do not write negative 10% because it's an absolute value. All right. So that was the uncertainty. One more thing about your measurements is that, again, all of these things that we are learning, that we learn in this unit, they might seem like they are very different from each other. But again, these are just like different types of measurements that we do in chemistry. So density is another type of measurement in chemistry. So density just measures the amount of mass in a specific volume of a substance. So the unit for density is going to be grams per centimeters cubed. This is the unit that we use for solids. And then if you are measuring the density of a liquid, that's going to be grams per milliliter. We are given the equation to calculate the density of any substance in table T. And then remember that the density of any substance is very specific to that substance. So we can use the density to identify a substance. We are given the densities of different elements in table S. So if you are, and this is a very common type of question that you can get, you might be asked that a student calculated the density of this substance to be this, calculate the percent error. And they might not give you the actual density. That's because the actual density is given in table S. So you're going to have to go to table S to find the actual density. Okay. So looking at the equation of density, very simple. It's just density equals mass over volume. So the unit can also be derived from here because the unit for mass is grams and the unit for volume, if it's a solid, is centimeters cubed. And if it's a liquid, is milliliter. So that's where the unit is coming from. So if you want to rearrange this equation to find the mass or the volume, let me start with density equals mass over volume. So let's say I'm asking you to find the mass of something. We rearrange the equation. It's going to be very simple. Just multiply both sides by volume. That way we get rid of the volume on this side. And your equation becomes mass equals density times volume. So this is your equation to calculate the mass, right? Now, if you want to go ahead and calculate the volume using the same density equation, the easier way to derive that is to start with the mass equation. So I'm going to start with M equals density times volume. So now I'm looking to isolate the volume. So I am going to divide both sides by density. So density gets canceled over here, and we are left with volume equals mass over density. So this is your equation to calculate the volume using the density equation. All right. So very, very important thing to remember about density is that we always, sorry, very, very important thing to remember about density is that the density of water, liquid water, is 1 gram per milliliter. And sometimes what might happen is that they'll give you the density in grams per milliliter, and they might ask you to find the volume in centimeters cubed. So just remember this very quick conversion for the volume. 1 centimeters cubed is just equal to 1 milliliter. Okay, so if I give you 10 grams per milliliter, it is equal to 10 grams per centimeter cubed. All right, so let's look at a very quick example of calculating the density. So we are given the sample mass. So this thing right here is going to be your mass. I need to go back to the pen. Okay, so this is your mass. And then we have the volume of the water and then the volume of water and sample. What they did not do here is that they did not give you the volume of the sample itself. So what you're gonna have to do to find the volume of the sample is multiply these two. Okay, so you take the volume of water and sample and you subtract the volume of water from that thing to get the volume of the sample. So we do 21.5 minus 20.0. That gives you 1.5 milliliters. Make sure that you do not get rid of the 0.0 after the 20, because we have to take care of the sig figs in for any density questions, and we'll talk about why in a little bit. So then you can just go ahead and plug these numbers into the calculation for density. So the mass is 10.23 grams, and the volume is 1.5 milliliters. So this is going to give you about 6.82 grams per milliliter. Now, as I mentioned earlier, we have to take care of the sig figs for the density problems, and here's why. If you do not take care of the sig figs, what you notice here is that our answer has 3 significant figures. So here's the answer, and this one has 3 significant figures, 3 sig figs. However, if you look at the 2 values in our question, the one at the top has 4 sig figs, and the one at the bottom has 2 sig figs. So 4 sig figs is fine. What we are saying about this number at the bottom is that our answer is more certain than the given measurement. And this is not possible. We are getting these 2 values, the mass and the volume, from what we measured in the lab. So our answer, whatever we calculate using these 2 numbers, cannot be more certain than what we calculated in the lab. So our answer must be in the correct number of sig figs. So the least number of sig figs that we have in the measurements is 2. That means our answer must have 2 sig figs. So in this case, that's going to be 6.8 grams per milliliter. All right. So always, 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 even if the question does not say that, always take care of the sig figs for your density problems. All right, moving on to the last thing that we want to talk about for measurements, and that is moles. So mole is the standard international unit to measure the amount of a substance. And we can remember the different conversions that we can do with moles using this quick triangle that we talked about in class. So the top of this triangle represents the moles. On one side, we have the mass. On the other side, we have the number of particles. So number of particles could represent the number of atoms, or it could represent the number of molecules. So when I give you a question about number of particles, I might not say number of particles. I might just say find the number of atoms, or I might say find the number of molecules. So just remember that we are talking about the same thing, and the conversion factor is going to be the same. All right, so if we are trying to calculate, if you're trying to go from moles to number of particles, number of atoms or molecules, whatever, the conversion factor that we use is 1 mole has 6.02 times 10 to the power of 23 particles. This very specific number came from the Avogadro's law. So this number is called the Avogadro's constant. So Avogadro told us that if you take the 1 mole of any substance out there, that 1 mole of that substance is going to have this specific number of particles. So this is the conversion factor that we use to go between moles and number of particles. We'll do some maths to figure out what it looks like in calculations in a bit. If you want to go from moles to mass, then we say 1 mole is just equal to the molar mass of any substance. So the molar mass in this case, for now, we have only talked about the elements. So remember that the molar mass of the elements is just its atomic mass, because molar mass is the mass of 1 mole. The mass of 1 mole. So if you want to find the molar mass of, let's say, oxygen, just go to your periodic table and see what the atomic mass is for oxygen. That's going to be the molar mass of oxygen. 1 mole of oxygen, by the way. If you have 2 atoms of oxygen, you're going to multiply the given atomic mass by 2. All right, so let's look at some questions. If I ask you how many grams do we have in 4.5 moles of carbon? The first thing, we're going to use dimensional analysis for the mole problems. So the first thing that you're going to do is determine your conversion factor. So because in this question, we are going from grams to moles. So remember, grams means mass. So sorry, we're going from moles to grams. So going from moles to grams, the conversion factor that we want to use is the molar mass. So you go to the periodic table and you figure out what is the mass of 1 mole of carbon. So using your periodic table, you're going to figure out that 1 mole of carbon has 12.011 grams. Okay, once again, this is your molar mass. So this right here is your conversion factor. So we're going to use this conversion factor. The second thing that we do in dimensional analysis is we start with what's given in the question. So in this case, we are given 4.5 moles of carbon. So that's going to be 4.5 moles, and then we multiply that with our conversion factor. So now remember, we have to make a decision about what we want to put at the top and what we want to put at the bottom. So do I put 1 mole of carbon at the top or at the bottom? Remember what we said about dimensional analysis. We want to cancel out the moles. So that means I want to go ahead and put 1 mole of carbon at the bottom. That way I can cancel the mole with the mole. All right. And then I'm going to put the 12.011 grams at the top. And we do the math, 4.5 times 12.011, and that is going to give us 54.0495 grams. For the mole problems, you technically do not have to take care of the sig figs unless the question asks you to take care of the sig figs. All right, so here's another problem. If I ask you how many molecules do we have in 4.2 moles of sodium chloride? Now, we are going from moles to number of molecules. So that means we're going to have to use the Avogadro's factor, Avogadro's constant. So your conversion factor in this case is going to be 1 mole of sodium chloride is going to have 6.02 times 10 to the power of 23 molecules. Now, please note that if the question is asking for the molecules, out of this whole thing, we're going to use the molecule. So we're not going to say particles or atoms. We'll say 6.02 times 10 to the power of 23 molecules, because that's what the question is asking for. And then we start with what's given in the question. So that's going to be 4.2 moles. And then we multiply this with the conversion factor. So remember, if you want to cancel the moles, we are going to put 1 mole of sodium chloride at the bottom. So the mole cancel out with the mole. And then we are going to have 6.02 times 10 to the power of 23 molecules, which is not going to fit. Well, it kind of fit. And then we just do the math. 4.2 times 6.02 times 10 to the power of 23. So that gives us about 2.707 times 10 to the power of 27 molecules. So remember that you have to write your answer in the correct scientific notation. So your answer should not be 27.07. It should be 2.707, because remember, your coefficient for scientific notation must be between 1 and 10. Alrighty, so that wraps up our measurements unit. Happy learning. I'll see you all in the next one.